Hey everybody, welcome back to another round of astronomy. What is the mechanism responsible for the volcanic eruption? Go ahead, answer the question. Yeah, remember that last video we were talking about densities and convection and the idea that the difference in densities down in the mantle of the Earth gives rise to these convection currents which drive the mantle through cracks in the Earth, and that's how we get things like volcanoes, okay? Or eruptions for that matter. Okay, cool. So we're going to continue on that path now, and the idea that we're going to look at today is how does the surface of the Earth change? Okay, so so the Earth is what we consider to be a quote unquote living planet. Maybe a better way to say this is that we consider it to be geologically active. So volcanoes are one way that we see geological activity on the Earth. Question I have for you is, can you think of some other ways that you see the surface of the Earth change? Hey, you got it? Yeah, good. So of course I already gave you the idea of volcanoes. Here's another picture back from 2018 about Hawaii, right? You have Kapoko Bay, right? This wonderful area, inlet that my understanding was it was a wonderful beach. And after this eruption or this, eruption might be a little bit strong of a word, but after this magma pushed through the surface and invaded some of that land space, it actually filled in the bay. So this is the same bay taken from a different angle after the lava flow kind of went through the area. And you can see that this entire region now has been completely filled in. I'd have to go back and check, but I want to say it was something like a couple square kilometers of new land was actually formed because of the mantle pushing up and covering some of the current landmass. Kind of cool, right? So there's other mechanisms by which the surface of the Earth changes. Today, we'll spend the majority of the time talking about tectonic plates simply because of, first of all, the effects on the surface of the Earth and also some of the telltale signs of tectonic activity. So we'll go there. And then the other one, perhaps that you're more familiar with and you might have mentioned, is this idea of erosion. Now that is not as quick as, for example, tectonic plates or volcanoes, but it is still a way by which the surface can change. So we'll discuss those today, and then hopefully we'll carry on the next time talking about the Earth and maybe even the moon. Okay, you ready for it? Good. Volcanoes, I don't have much to say. We've already talked about it pretty much to the extent that we need to. It's a location on the Earth where the crust is cracked, if you will, and because of that crack or that separation in the crust of the Earth, some of the underlying material is driven to the surface by the convection currents. So I don't really have much more to say about volcanoes per se, but these tectonic plates I think are pretty cool. Okay, so I'm going to do something that I usually, you shouldn't do, but I'm going to go ahead and put this wonderful quote up on the screen for you. And let me read it out to you. There is always a strong inclination for a body of professionals to oppose an unorthodox view. Such a group has a considerable investment in orthodoxy. They have learned to interpret a large body of data in terms of the old view, and they have prepared lectures and perhaps written books with the old background. To think the whole subject through again when one is no longer young is not easy and involves admitting a partially misspent youth. Furthermore, if one endeavors to change one's view in mid-career, one may be wrong and be shown to have adopted a specious novelty and try to overthrow a well-founded view that one has oneself helped to build up. Clearly, it is more prudent to keep quiet, to be a moderate defender of orthodoxy, or to maintain that all is doubtful, sit on the fence, and wait in statesman-like ambiguity for more data. Parenthesis, my own line until 1959. Okay. Now this came from Edward Bullard, and he was the one to first introduce this idea of plate tectonics. What he was saying is he's a bit hesitant. There's always an inclination for a body of professionals to oppose an unorthodox view. What he's really saying is it's really hard for people to accept new ideas, even scientists. And then he goes through and explains, well, you've invested your career going one way. It's hard to admit that you're wrong. Okay? Or it's a risk to try something new. It's the other place where he's saying. But fortunately for us, he kind of pushed through that hesitancy and he came up with this brilliant idea. Let me give you a picture from one of his papers. This reflection was written in 1975, well after he had established himself. But let me give you a picture from a paper that he published in 1965. Okay? And you probably notice what is sitting in front of you here. Yeah, you see it? You have South America and you have Africa. Okay? And you notice that they've been placed together like a puzzle piece. Now, previous to Edward Bullard, what had happened was people kind of fiddled with placing the continents and putting together. Okay? Trying to figure out, treating them like puzzle pieces and seeing if they could fit together. And they always ended up with these kind of cartoonish kind of final results. And I say cartoonish because they needed to adjust the coastlines. They needed to kind of mash the coastlines together or deform them a little bit to get everything to really fit together in a coherent manner. What Edward Bullard decided to do was he said, wait a minute, let me pretend that I can drain the oceans. And rather than considering the coastlines of the various continents, let me think about the continental shelf. Okay. So you might be familiar, but you have, for example, the landmass, the United States, and you have the coastline, say, over in Washington, D.C. or over in California, and that's all fine and dandy. But if you could actually go beneath the surface of the ocean, you'll notice that there's actually a precipitous drop-off. Okay? So you can still, you can go a little bit a ways from the coastline, I want to say 50, maybe even 100 miles, before you really get a huge drop-off into the deep ocean. Okay? So the issue is he said that drop-off, that region before the really big drop-off is called the continental shelf. Okay? It's still, if you will, a piece of the land, but it's underwater. Okay? And what Edward Bullard decided to do was to try to fit the puzzle pieces together with the continental shelf. And so what you're looking at here is the result of that process where he tried to get things to fit together. And what was surprising to people is that the regions, for example, Africa and South America, fit a lot better when you did it according to the continental shelf. Okay? This actually gave people confidence that maybe this was actually the right way to go. Okay? And so Edward Bullard, he had this other comment. This is at the end of his paper from 1965. He said, only two explanations have been proposed for the approximate fit of the continental blocks. Either the fit is due to chance similarities and is on par with the similarity of the coast of Italy to a boot, or the continents were once united and have separated with the formation of the Atlantic Ocean. Okay. So he said, you've got two possibilities here. Number one, it's happenstance. It just randomly occurred, much like how Italy resembles a boot, or maybe Louisiana for that matter. Okay? Just chance similarity. But he says, or I propose that they once were fitted together, that they started out together and since have separated. And that's the idea of plate tectonics, is that land masses such as Africa and South America at one point were together and have slowly drifted away on their respective plates. Now he goes further than this. Okay? Later on in the same paper, this was in the conclusion section, what we call the conclusions and discussions, but not only does he propose a model, hey, things used to be fitted together and they must have since separated out, so that's the conceptual model, he also gives us some future predictions. Okay? He said this: it is perhaps more profitable to approach the problem of significance by considering other aspects of the fits. Okay? If the continents were once joined, then not only the shapes, but the ages, structures, and petrology of the rocks must match across the joins. If they do not, the probability that the fits are due to chance is negligible. Excuse me, I put a not in there. Big difference. Let me say that again. If they do, the probability that the fits are due to chance is negligible. In other words, he's saying, hey, okay, I fitted these together. If this is indeed the correct model, then we should see some similarities in rocks across the boundary of the two continents. Okay. If they were once physically close together, we should notice some similarities in the rocks, the rock formations, for example. Okay. That's what he's saying. So he's saying, go look at the rocks. Go study the various structures on the western coast of Africa, the eastern coast of South America, and see if you get the same structures. See if you get the same types of rocks. And so indeed, what ends up happening, this has been done. The yellow areas, if you notice in Africa, so you have the Sahara and the Horn of the Horn of Africa is over here, isn't it? You have the Sahara, and you have rock formations that if you put South America and Africa together, you have rock formations that actually span the gap between the two continents. Okay. That's pretty cool, right? In 1965, he says, hey, if this is the model, then this is one of the predictions, and people went out and actually found it. Science is awesome. Okay? But there's more. You ready for it? Here we go. So another study of rocks is looking at what's called paleomagnetism. Okay? Magnetism, just like you would normally think, magnets. Okay? Paleo is looking at the magnetism of the past. And let me give you an idea about how you could actually perform this. Say I have two compasses, and I better indicate where north is. So let me put north in, and you know that the compasses will point to north. So if the North Pole is located by this X, then the compass directly here, this grayish one, is going to point north. This dark gray one is also going to point north. Okay? And you notice that the orientation of the compasses are slightly different. And why is that? Yeah. It's because the compasses are located at different locations. Okay? If I put these two compasses at different locations and compare the direction that they both point north, but one of them might be angled with respect to the other. Okay? That's the first key. Now let's imagine for a second, rather than these two compasses being at two different locations at the same time, let me think of them as being a single location at different times. So let me overlap those two for a second. Okay? So I'm thinking single location at different times. And that's really what paleomagnetism is looking at. Imagine for a moment that you dig down into the ground. Okay, we're going through different layers of rock. beneath our feet. Okay? And what we can do is we can look at the compasses in each layer of rock, in each layer of sediment, if you would prefer. Okay? Now you say, well, wait a minute, Greg. It's not like the Earth buries different compasses at each layer of rock. And I agree. Okay? We don't have actual compasses. What we have are iron filings, little tiny pieces of iron. And you know that iron is what we call a ferromagnet. If you expose it to a magnetic field, it will align with that magnetic field. In fact, that's primarily what compass needles are actually made out of. Okay? You take a piece of iron, you magnetize it, and then it will point to north. So the little iron filings that are in the layers of rock are like tiny compasses. They will adjust and point north when they're free to move. Okay? So if they're free to move, they'll align with the Earth's magnetic field. Okay? So one of the cool things that we have found is that as we go further and further down in the various layers of sediment, of rock, we find that the compass points in slightly different directions. Well, that's weird, right? What's going on? What's happening is just like our demo here. Okay? What's happening is that you can think of the layer of rock changing positions with respect to the North Pole. In other words, back in the distant past, the further down you go, okay, this layer of rock was at a slightly different location on the surface of the Earth. Its iron filings were pointing at north, and then they locked into place. So they're pointing north, and then they get frozen in place so they can't rotate anymore. Okay. Later, another layer of rock gets deposited on top. The iron in that layer of rock aligns with north, locks into place, okay, is no longer allowed to rotate. The next layer, the next layer, the next layer, the next layer, the next layer. Okay? So what we're looking at as we go down further into the layers of rock is that we are actually getting a record of, first of all, how far in the past, the further down, the further in the past we're looking, and also what direction, where that layer of rock was with respect to the North Pole. Pretty cool, huh? So let's put this together. First of all, how can I deposit new layers of rock? Go ahead, give me an answer. It's not by accident I gave you a volcano video at the beginning, right? You are looking at essentially molten rock. Inside this, there are tiny pieces of iron. Okay? Rock has some iron in it as well. And so what's happening is this molten rock, when it's liquefied, those iron filings are free to rotate and align themselves with north. But once that rock cools down, it locks the iron filings into place. Right? They won't rotate anymore. It's not a liquid, it's a solid. And so that's how you lock it into place. And then you put layers, you get new layers on, et cetera, et cetera. So here we go. Paleomagnetism. What this allows us to do is consider the location of a landmass, okay, with respect to the North Pole, and the iron filings lock into place. Sometime later, say millions or tens of millions of years later, that landmass has shifted, a new layer of iron gets deposited, creates a new layer of rock, and those iron filings lock into place. Keep going forward in time, a new layer, you get a new direction for the iron filings, a new layer. So what this allows us to do is kind of track where the landmass was today and yesterday and further back in time. That's cool, right? Let me give you another example. Okay, so that's paleomagnetism. And we can track back in the past, according to our model, where these land masses used to be. Let me give you another example. Okay? Now this is called the Hawaii Emperor Seamount Chain. And let me explain this figure off to the right-hand side first. Okay? What you have are, I'll use the orange as what we call the tectonic plate. Okay? And the blue arrow is just to indicate the direction that it's moving. Okay? You have the orange tectonic plate, and it's surfing, if you will, on top of, I'll just say the mantle. Okay, there's some other terms like the lithosphere and the asthenosphere, and so there's some other stuff. I'll just say, okay, you've got the tectonic plate in orange surfing on top of the mantle. Okay. Now, what happens? Okay, for the Hawaii Emperor Seamount Chain, the mantle itself is not a single temperature. Okay? Usually, the convection currents help, move stuff around and keep stuff kind of reasonably stirred. But the Earth is huge. Okay? You're not going to get this uniform temperature all over the place. So what happens is underneath Hawaii in particular, there is a mantle plume. There is a spot underneath the island of Hawaii that is particularly warm in the underlying mantle. The other issue is that the crust is a little bit thinner, and the combination of those two means that the mantle punches up through the tectonic plate, okay, and creates a volcano. But that top plate moves. Okay? That orange plate is moving according to our model. And so what happens? Later, sometime later in time, you notice this mountain peak has shifted to the left. Okay? And it's not by accident. This mountain peak has now shifted off of the mantle plume. And so what happens is that mountain peak is no longer an active volcano. It has gone dormant. It has gone extinct. Okay. But what else has happened is that a new location is over the mantle plume. And so a new mountain now forms, a new volcano. You can liken this to taking a piece of paper and slowly pulling it over, say, a candle or a blowtorch. As you pull the piece of paper over the candle, you'll create new the old scorch marks will stop burning, and you'll create new scorch marks. Cool, huh? So here's the status of where we stand today. As I've mentioned, GPS has given us a good idea about the motion of the tectonic plates. And you can see that the Earth is divided up into maybe a dozen plates or so. Some of them rather large, like the North American plate. Some of them rather small, like the Indian plate or the Caribbean plate. And here as well, you notice that the red lines give you the directions that the various plates are moving. So for example, down the middle of the Atlantic Ocean, you have a series of plate boundaries that are pulling apart from each other. Okay. Whereas, for example, on the ring around the Pacific Ocean, you have a lot of plates, namely the Pacific plate, running into other plates. Okay? So spreading from the Atlantic Ocean, you have locations on the Pacific Ocean where they're kind of crushing back together. And that should make some sense. If you're if you're bringing material up in one location, it better darn well better sink down somewhere else. Okay? So you have places where they're pulling apart, and you have places where they're bashing together. Okay? Let's talk about some of these locations. Okay? So plate tectonics. We'll say the boundaries or the cracks where mantle is being introduced from the Earth's interior are referred to as rifts. Okay? And the main one that you notice on the Earth is what is called the Mid-Atlantic Rift. Okay? It's a boundary between plates where new mantle is being introduced and pushing the two plates apart. Okay? Now, places, boundaries, cracks, where two plates are coming together are called subduction zones. They are locations where a less dense plate slips above the more dense plate. Higher density goes down, lower density will float to the top. And so subduction zones are that place where two plates, one goes beneath the other. In those locations, you get what is called a trench. Generally, the land that's floating on top of the plates crumples together, and you get a specific area that is profoundly deep if these occur over the ocean. Okay? Some of the deepest places in the Pacific Ocean are oceanic trenches where two plates, one is sinking beneath the other. Okay. So, for example, there is at least one place I'm aware of where you can see the effects of the rift on landmass, okay, on actual land. Okay. Oh, excuse me. I've got this. You can think of the crust, the thing that you and I are standing on, as kind of surfing on these tectonic plates. Okay. So we're moving at roughly 2 to 10 centimeters per year. It depends on which plate and which way you're moving, but that's kind of the general speed, about how quickly your fingernails grow. Okay. Not very fast, but considering the fact that you're pretty much moving the entire crust of, I don't know, North America, that's a lot of material to be moving. Okay. So here's one place that I can think of where you can actually see the two plates pulling apart. In Iceland, it's right on the Mid-Atlantic Ridge. And so, oh man, I don't know if I can pronounce this. Thingvellir National Park is one of those locations. What you're seeing here is actually the rift between the two plates slowly pulling Iceland apart. And there's also some really cool pictures. For example, you can go in some of the inlets or some of the water-covered regions. And again, you can see this rift that progresses down into the water. And you can kind of scuba dive in there. No, don't worry, you're not going to hit the actual mantle. That's something like 100 miles beneath the ocean. So you got to really go through the ocean. You got to go through the rest of the crust and then kind of get to the plate boundaries. Of course, you also have places where the plates come together. Okay? So here's an example where plates are pulling apart. Here's an example of where plates are pushing together. And again, the crust kind of surfs on the top. And so when the plates crush together and one subducts, the crust on the surface of those plates crumples together. And so when you get that crumpling, you can get a lot of mountain ranges. And again, you'll notice, if I go back a slide, you'll notice that, again, Iceland, right on the Mid-Atlantic Rift, Mid-Atlantic Rift or ridge, you could call it a ridge as well. I'll call it ridge. I seem to be having problems saying rift. Okay? The Mid-Atlantic Ridge. Okay? But you'll notice that there's areas, boundaries where two plates go together, like the Nazca Plate and the South American Plate. Right here on the western coast of South America, that's indeed where the Andes Mountains are. Or, for example, you have the Indian Plate hitting the Eurasian Plate. And that is, the cause of the Himalayas. The tallest mountains in the world are due to the Indian Plate crashing against the Eurasian Plate. Same thing, you have a lot of mountainous regions in Japan, for example. Again, you have the Pacific Plate crashing into either the North American or the Eurasian Plate. Incidentally, this is where a lot of our trenches are. Okay? Again, where two plates are coming together. And also notice that plate boundaries tend to be the locations where you're going to see magma or mantle being introduced. It's not by accident that the Pacific Ocean along this boundary is sometimes referred to as the Ring of Fire. Shark bait, hoo-ha-ha. Okay? This plate boundary represents a location where a lot of mantle can come up to the surface. It's a gap in the plates, if you will. And so you end up with a lot of volcanoes generally along the plate boundaries. You'll also notice that these tend to be places that are prone to earthquakes. That is, again, because these plates don't smoothly go past each other. They sometimes stick. Okay? And so, for example, right here in the North American Plate and the Pacific Plate, rather than them crashing together and forming a mountainous region, rather than them pulling apart and forming a ridge, here they're slipping past each other. And so that forms what's called, I believe, a slip fault. So they stick, and then every once in a while they slip. And you get, an earthquake. Okay? So earthquakes, in the context of talking about tectonic plates, earthquakes are simply plates that slip past each other during their motion. Okay. This is a current map from the U.S. Geological Society. Age of the oceanic lithosphere. If you prefer, you could say the plate tectonics. And the areas that are colored in red are just showing you where new material is being introduced at a ridge. And then as you go into the greens, yellows, and blues eventually, you're going older and older crusts or older plate material. And so you see things like the newest material is being presented at the Atlantic Ridge or just off the coast of California, which is incidentally the San Andreas Fault, the location where the plates are separating, and all the way down into the South Pacific Ocean. Okay. The oldest plates, you notice, are actually right around here in the Mediterranean. Okay, those are some of the oldest plates in the world. Okay. So not only do we have an idea about where the plates were in the past, but now knowing the current direction, the current speeds of the plates, we can see or project where they're going to be in the future. So that's all I have to say about plate tectonics. So now we have two methods by which the surface of the Earth can change. You have volcanoes, which can just pave over things and create new land masses. And this one tends to be even more extreme. Okay? Plate boundaries, giving you ridges, giving you trenches, and also giving you boundaries of volcanoes around the edges. Okay? You can also crash things together to form mountain ranges, etc., etc. The last one, which I'm probably sure you're familiar with, and this is a one-slide kind of thing, is what we call erosion. Okay? And this one, as you're aware, is the fluid transport of solid material, or rock if you want, material, soil, sand, rock. And you've probably experienced erosion. I've had Nora and Graham crying about erosion. Okay? When they build a sand castle at the beach, and that big wave comes in, and all of a sudden, sand castle is no more, right? That you've witnessed erosion. The water is carrying those particles of sand and redistributing them. Of course, if we wait long enough, if you do that long enough, you end up carving out things like the Grand Canyon. The Colorado River pulls enough of that material and moves it downstream that eventually you carve out the Grand Canyon. Doesn't have to necessarily be water. Water is particularly efficient for erosion processes, whether it be lake fronts or rivers or even rain, gradually wearing away things. But you could also do it with the wind. So over here we have a sand dune, and you notice that it used to be kind of a circular thing, probably an impact crater of some sort. Okay? And then what happens is, as the atmosphere, as the winds blow, you start weathering away the edges. You start, instead of getting a nice round shape, you start getting dunes, for example. Or you get these wave patterns in the middle where material has been taken from the surface and deposited inside. Okay? Of course, you're probably already familiar. This is not the Earth. Okay? This is a picture of Mars. Okay? So even we see these erosion processes not only on Earth, but we see them on other planets as well. Which is why we're going to be using some of these features to kind of look at other surfaces. Okay? So in summary, we've got a couple of geological processes. We've got volcanoes. We've got plate tectonics, which give us ideas about ridges, trenches, mountains. And then we have erosion, which can give us things like canyons and valleys or dunes. Okay? The first two, I'll say, are associated with the molten interior of the Earth. Okay? So if we see these processes ongoing, we infer that the interior of the body, the planet, is molten, is still liquefied. Okay? When we see things like erosion, we can assume or infer that the planet has water or has some sort of appreciable atmosphere. Okay? And where we're going to go with this is that geological activity depends on the molten core. If you have a molten core, you can do these geological processes, and therefore we consider you to be a living planet. If you are geologically inactive, if we do not see volcanoes, if we do not see plate tectonics, we infer that the core is solidified and you are what we would call geologically dead. Okay? So I think I'm going to leave it there. I think that's probably good enough for this video. I thank you for your attention. Keep up the good work. I'll see you next time.